Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And good day. Hi guys, we meet again. Okay, we will continue our class using as usual as an online video. Um, Today we will look at this section. We will look on still a Brayton cycle, but with modifications based on the intercooling and also reheating. Okay, let me share my slide. Okay, we look on the slide. Okay, Brayton cycle with intercooling, reheating, and also regeneration. As you all know that the topic of modification with regeneration uh, has been covered in last uh, class. So today I will discuss or talk more on the intercooling and reheating. Okay, as you all see in the slide, this is a schematic diagram of the gas turbine engine, or in the ideal analysis, we analysis it based on the Brayton cycles, or another name as a Joule cycle. So in here we put on the intercooling and reheating. Okay, as you see, if you want to put the intercooling, that means the intercooler must be in between compressor number one and compressor number two. So by it mean when you modify the system with intercooler, that means you must have a multi-stages compressor. Okay, this is a compressor one, actually also named as a low pressure compressor. Compressor 2 is also named or known as high pressure compressor. Okay, uh, and for reheating, we put a device called reheater in between turbine number 1 and turbine number 2. So it is as same as a compressor or intercooler. Turbine, when you put reheater, you also have to know that the turbine must be designed in multi-stages turbine. Turbine number one is also known as high pressure turbine. Turbine number two is known as low pressure turbine. And this is the regenerator. Okay, we have discussed this device and how the concept of this device been introduced to Brayton cycle. Okay, for the TS diagram, if you look on the schematic diagram, state number 1, state number 2, 3, and 4, this is a compressor. Okay, and this is a multi stages compressor. For process number 1, that means work has been put required through the compressor. So at this stage of compressor 1, what happened? The temperature is increasing because it has been compressed, and then the temperature will be reduced because of intercooler. Okay, but the interesting concept for the intercooler because it will reduce the temperature, but the pressure is the same, and it will also reduce the volume of the molecule. So in this stage, it will be compressed again to compressor number 2. So when it comes to state number 4, the air that has been inlet into the system of compressor within the intercooler will have more of the compression air or compression gas. Okay, so before it will be able to combust in the combustion chamber. So after that, when it will go through the regeneration, at this point, heat also regenerate in this process to the compressed air, and then at point 5 to 6, heat also have been added here, and then the combustions will be combust in the combustion chamber. Okay, and all the energy that has been created from the combustions in the combustion chamber will be passed through the turbine number 1, where in the turbine number 1, work has been created, and the temperature is decreased, and also the energy will also be decreased because the energy has been turned for the chemical energy to rotating energy or mechanical energy, and then to electrical energy. So because of the less of energy, less of the temperature, pressure, what happened, the gas, the product that come from the turbine number 1 will be uh, passed through the reheater for the reheating process. So at this reheating process, what happened, this product will be heated up to the temperature, a certain temperature, at the same pressure, and then another work from the energy will produce from the energy that has been heated, from the energy that has been treated by the flow or by the gases, that product gas that come from the reheater to turbine number 2. Okay, so we in this system we have two work output. That's mean at 6, state number 6 and state number 7, and also state number 8 and state number 9. So and then this product will be passed to the regenerator, and the heat will be transferred to the transfer in the heat from the product gas will be transferred to the inlet gases, and then all the product will be come to the atmosphere. So this is number 5. Okay, this is a schematic. This is a TS diagram for the Brayton cycle with intercooler, reheating, and regenerations. Okay, you have to remember, or you have to know how this process happen, and also you have to know how to draw the schematic diagram and also the TS diagram. Okay, the important one, another important thing is we look on the minimize work input to the compressor, and also the maximization maximizing work output from the turbine. As you see in the TS diagram, the pressure in the compressor, that means the ratio pressure P2 over P1 actually is equals to P4 over P3. Okay, that is about for the compressor. And also happen to the turbine where P6, the maximum pressure ratio over the minimum pressure P7 is equals to P8 over P9. Okay, this is a ratio pressure of the turbine. Okay, the thing here, you have to also know that when we talk about the multi-stages compressions with intercooling, the work actually required to compress a gas between two specified pressures can be decreased. That means by carrying out the compression process in stages and cooling the gas in between. So what happened with this process happen? This keep the specific volume as low as possible for we doing the process of intercooling. For the multi-stages expansions with reheating, it will keep the specific volume of the working fluid as high as possible during an expansion process through maximizing work output. That is reason why we put intercooling in between compressor and reheating or reheater in between turbine. But for intercooling and reheating happen, you know that it always decreases the thermal efficiency unless they are accompanied by regenerations. Okay, why it happen? This is because intercooling decreasing the average temperature at which heat is added, and reheating increases the average temperature at which heat is rejected. Okay, this is the diagram that explain the thermal efficiency that's been decreased when we put intercooler. Okay, and this is show the TS diagram when you put or you make it, the number of compression and expansion stages increase. There are too much compressor, many compressor that's been put in the system, many turbines that's been put in the system, and at the end, or it will generally approach the Ericsson cycle. Okay, but in this course, we don't learn or you don't be learn about Ericsson cycle. Okay, these are some of the examples that I want to discuss. But I think this example you can do it yourself. Okay, I want to show you another examples that much more simple from this example, or this is can be used. And if you got any problem doing this example, you can ask me anytime. Okay, I go to next slide for showing the example. Okay, click on this slide and Windows. Mm, wait, where another picture? I will share you one of the slide uh, uh, based on the uh, notes that's come from the one of the university. Here, okay, saya tayang time. Okay, let's look on the example Brayton cycle with intercooling, reheating, and regeneration. Okay, in this case, in this problem examples, it give a regenerative gas. Okay, the question is about a regenerative gas turbine with intercooling and reheat operates at steady state. The air enters the compressor at 100 kilopascal, 300 Kelvin, with a mass flow rate of 5.807 kilogram per second. The pressure ratio across the two stages compressor is 10. The pressure ratio across the two-stage turbine is also 10. The intercooler and reheater each operate at 300 kilopascal. At the inlets of the turbine stages, the temperature is 1400 Kelvin. The temperature at the inlet to the second compressor stage is 300 Kelvin. And it also gives the isentropy efficiency for each compressor and turbine stage is 80%. The regenerator effectiveness is 80%. Determine the thermal efficiency, the net power developed in kilowatt. See the bed work ratio. Okay, first of all, you have to know the first sentences. The first sentence. The first sentence show that this is a regenerative gas turbine problem. And this is not the simple or ideal gas turbine, but this is a Brayton cycle with modification of intercooling reheat. And also in this Brayton cycle, it also said that the it have the regenerator effectiveness. That means regenerator has been put in the system, and also it also wants you to know how to analysis if the isentropy efficiency of compressor and turbine stages has been given 80%. So as I discussed and told you last class or previous class, when you saw this example that have mentions the isentropy efficiency of compressor or turbine stages. So what you have to do is you must find the actual value of the temperature of turbine and also compressor, and put it or take actual value of temperature into your calculation analysis, and got the and lastly get your answers based on the actual value. Okay, step number one, what should you do? Draw. Okay, draw the diagram that represent the system. So what I have mentioned right now, you have intercooler, the system have intercooler, that is it it plays in between compressor 1 and 2, and it also have reheater, and it plays in between turbine number 1 and turbine number 2, and so it also have it exchanger called regenerator after the turbine number 2. Okay, this is all the schematic diagram that you have to know how to draw it. Okay, and then for under or for better visualize what happened during the cycle, you also have to draw TS diagram for these regenerative cycles that have intercooler, reheater, and also regenerator. So this is a graph of TS diagram based on the three modifications. But this is not for the ideal. This is for the actual. That's why process 1 and 2 have a dot line and straight line. Okay. Also for turbine, you have two situations: dot line and straight line, dot line and straight line. That's mean dot line is represent the ideal process of compressor. Dot line for the 6 to 7 and 8 to 9, as that is represent for ideal process for turbine. So you, in this analysis, you have to find T7, T9, T2, T4. And these all values that I mentioned, you have to take it and put in your analysis and get your final answer. Okay, okay. In this step, it show how to prepare all the given data in the tables manner. Okay, and then try to assume, or you have to make your assumptions. Four assumptions that has been made. Number one is neglect all kinetic energy and also potential energy. Number two, assume this is air standard assumptions because the working fluid is air, so we assume it as a air standard assumption. Number three, when you assume air standard assumption, so you have to assume air is an ideal gas with specific heat at room temperature. So what it means, you have to take the value of Cp and Cv for air at room temperature. Okay, and also lastly, you have to assume the formula that you want to use is SSSF. That means steady state flow energy equations. Okay, okay. Not non-flow. This is steady flow energy equation. Okay, based on the calculation, it want you to find thermal efficiency. Based on the thermal efficiency of this system, you know the basic formula is W net over with Q in. In this case, Q in have two. That means Q in number one and Q in number two. Okay, look at the picture. Q in number one is in the combustion chamber. Q in number one. Q in number two is in reheat combustor because we made the modifications. That means you also have another device called reheater. So we heat in that devices. We also put heat. Okay, add heat in. That means Q in have two. Okay. So from there we find W net. W net come from W turbine minus W compressor. So turbine have two stages: work from turbine number one plus work from turbine number two, work from compressor number one plus work from compressor number two. And then rearrange these equations based on delta H, because this is we put it as a closed system. What happened? Q minus W is equal to delta U, and then you simplify that and you will get delta H. From here, H, because this is not water or refrigerant, so the method of solutions is based on the formula. So from delta H, you must convert it to delta T. Okay, you know the formula of enthalpy, convert it to the Cp delta T. So from there, work net will become Cp delta T, followed by equation number 2, and it will become question number 3. Okay, from here, this is for W net. For Q in and Q in 2, same as what I have mentioned right now, delta H, and then simplify it in the formula Cp delta T, and then this is equations that you have to find its all the values to get Q in 1 and Q in 2. Okay, okay, now you got all the equations that you want to use, so you have to find the temperature from state number 1 to state number 10, I think. Okay, yeah, for T1 it has been given. Okay, but for location T2 or state number 2, this is where the compressor number 1 take place. So because it said the compressor efficiency have 80%, so you have to use the efficiency of compressor based on the formula at ideal over initial, enthalpy ideal over enthalpy initials. Simplify the equations, then you can find T2. Okay, using all these value. Okay, I think to get to T2, you have to find T2S first. Okay, T2 has is come from the dot line of compressor. Compressor we assume as the isentropic, so this relationship between temperature, pressure, and temperature ratio and temperature pressure can be used. So using these equations, you will get T2S, substituting all these back into equation number 5, and then T2 will get the answers. Okay, T2. Okay, for T3 is given. Okay, for T3 is given. So T4 using as the same as we have discussed in upper previously. Then from here, equation number 6, same as what we have discussed earlier, and then T4 will get the answers. Okay, then to find the temperature at location or state number 5, we have to make use of the regenerator effectiveness. Okay, we see in the pictures T5. Okay, T5 here. So you have to use the equation or effective regeneration effectiveness. Okay, it gives in the questions. So using that formula of regenerator effectiveness, so these equations, then from there T5 is you simplify the equation, you will the T5 is like this equation number 7. Okay, but here in here you will have to find another uh, T9. Okay, T9. So just if you don't get T9, just go for the another state to find the answer. Okay, for T6, it has been given. T7, this is turbine. Turbine efficiency has been given. So using the turbine efficiency equations, from here, come out with T7 is equals to blah blah blah. Question number 8. And from there, because isentropic turbine has been assumed as the isentropic, so you can use this relationship of isentropic formula. So you can get T7 as ideal. Okay, and put this value in equation number 8. Then you come with equation. You come with answer of uh, temperature at point number 7. Okay, point number 8 or temperature number 8 has been given in the question. So as similar to the above explanations, so you can get it T9 as we discussed early. Okay, the process is like the same. So and then T9 will get the answer. Okay, and then go back to T5 in equation number 7. We have got a temperature at state number 9. So from there, put all the value and then T5 will get the answer. Okay, this is all the answers that been tabled in the table T5. And based on the equation, firstly the equation thermal efficiency, put all together all the values, and then lastly you will get the thermal efficiency is 0.443, or times by 100, it will give you 44.3%. That is answer for number 1 A. Okay, for B, it want you to find the power. Okay, power, that means you have to time work net time m dot air, because the unit power is kilowatt. So m dot air has been given kilogram per second is units, and then time joule per kg, and from there you will get the answers based on the unit kilowatt. Okay, this is the answer for the power of this system. Okay, and then C is bed word ratio. That means definitions ratio of compressed words to the turbine work. So based on the equation, this equation you have to remember because it don't give in the exam or in the, but you can look on the books. Okay, the equations. So based on it, you have got the value of work compressed in and also work turbine out. Okay, put in the equations, and then you will get backward ratio as 46.6%. Okay, I think this is a quite easy equation, easy solutions, easy problem. This is just straightforward. Please do it uh, time many times, and lastly you learn from the equation and analysis, and then from there I think you will get all the knowledge uh, based on the Brayton cycle with regeneration, reheating, and intercooler. Okay, think this all uh, for this time. Hopefully you get to know or some knowledge from this theoretical lecture, and also the analysis calculations example. And please do yourself with your problems and exercise. From there you will get something. Okay, that's all for this time. uh, See you in next lecture. Okay, assalamualaikum warahmatullahi wabarakatuh. And Have a good day. Okay, bye bye.